Imagine a material that is easy to produce yet extremely strong and flexible. Such a material does exist and is known as fiberglass. Fiberglass is in a family of materials known as fiber-reinforced plastic, or FRPs. Fiberglass was first discovered by the Phoenicians, Egyptians, and Greeks. They knew how to melt glass and stretch it into thin fibers. However, it was not until the 1930s whenever three individuals developed the protrusion process, which enabled large-scale production of fiberglass. Fiberglass can fit into two main categories, those with short fibers and those with long fibers. The short fibrous version is mostly used for insulation and for filtration. The long fiberglass is used for textiles and yarns. The composition of fiberglass is similar to that of glass. It is composed mostly of silicon dioxide, which, although in the unimolecular form is linear, when it forms into a lattice, it becomes tetrahedral. It is also composed in a very small part of sodium oxide, potassium oxide, and calcium oxide. This is silicon dioxide in a network solid. As you can see, it forms into a tetrahedral shape. This is because it is more enthalpically favorable for it to form into this shape than to have any double bonds between silicon and oxygen. Because it formed into this tetrahedral shape, it is only held together by intramolecular forces. Therefore, it is very strong. Fiberglass is created by a process known as batching. In the batching process, three different compounds are mixed together. The first is silica sand, which functions as the glass former. The second and third are limestone and soda ash. Both of them function to lower the melting point. After mixing, the resulting compound is then heated to form molten glass. Finally, the molten glass is passed through platinum bushings, which contain hundreds of holes to extrude the thin filaments. What happens next differentiates the short fiberglass from the long-stranded fiberglass. If it is long-stranded, then it undergoes the protrusion process.
Reels of unidirectional roving provide longitudinal tensile strength, or the strength along the length of the profile. Rolls of continuous filament mat, woven roving, or stitch fabric provide the profile with its transverse properties or its strength across the width of the profile. All reinforcements are first fed through preforming guides that will begin to shape the raw glass fibers into the finished profile. The glass is then pulled into a resin bath that saturates or wets out the reinforcements. The resin bath contains a mixture of resin, most commonly polyester or vinyl ester, pigments to add color, filler to enhance properties, and a catalyst to aid in curing or to turn it from a liquid to a solid. Surfacing veil is added to give the profile a resin-rich surface and enhance the appearance of the final product. The wet-out reinforcements now enter the heated pultrusion die. The heat begins the thermosetting reaction process that cures the finished profile. The cured profile is now advanced by a caterpillar-style puller to the cutoff saw, where it will be cut to its final length. This fiberglass can then be used for many different things, ranging from wind turbines to kayaks to surfboards and more. One of the most popular uses of fiberglass is to make fiber optics. Fiber optics is transmission of a signal through a cable by using light. We will now be hearing from Dr. Joanne Ye, who is a tenured professor of physical, biological, and molecular chemistry. She has published well over 100 papers in prestigious academic journals such as Nature and Science, and has gone to over 120 talks worldwide. To meet some advantages and disadvantages of carbon nanotubes.
Yes, so carbon nanotubes are single layer or single atom layer of carbon that's a sheet. Those are called graphene sheets, and the graphene is rolled up into a tube. The advantage of carbon nanotubes are that carbon, as you know, is abundant. Carbon nanotubes are also have various characteristics that can be modified. But carbon nanotubes have several disadvantages if we're talking about comparing carbon nanotubes to other material. So it's all dependent on the application. Overall, and in regards to medical health, carbon nanotubes have not been well studied because of the fact that they were discovered in the late 1990s. And being that carbon nanotubes can shear and they will break into small pieces, the likelihood of carbon nanotubes becoming very small nanoparticles can be quite high, I would think. And because of that, and because of the research that I've done with my collaborators at UCLA Medical School, which showed that any material that's made fine enough and small enough, and this is in the nanometer range, so from single to hundreds of nanometers, these materials, these nanoparticles in general, can be easily aerosolated, meaning that they can become airbound. And because of that, these particles can be breathed into the lung. And we've shown in that paper and other work since then, as well as other groups that's verified our results, is that these particles can get into the cells because of their size, and depending on their surface charge characteristics, as well as their dimension, and whether they're spherical or if there is a larger dimension in one direction. But if these are somewhat spherical and they're small enough in the 20 to 50 nanometer range, these can penetrate cell membranes readily. And once these nanoparticles get into the cell membranes, these are taken up and target the mitochondria, as well as vesicles, or that contain reactive oxygen species. And what can happen once these nanoparticles go through the mitochondrial wall is it starts to disintegrate the mitochondria from the inside out. And that starts to release, think of it as almost a cascade of reactive oxygen species, and start to completely destroy the cell. So it causes apoptosis of the cell. And what we showed is that particles of size, as I mentioned, around 20 to 50 nanometers, and especially if they were positively charged and single positive charged and neutral, these target the membrane because of the negative surface characteristics of the head groups of lipids. So these nanoparticles then are targeted to the membrane and can easily penetrate and starts to break down cells from the inside out. So certainly one of the disadvantage or one concern is that there's not been enough done in regards to studies about how safe carbon nanotubes are, and being that carbon nanotubes can be charged at their tips once it's, so for another line of research in my lab, we've etched carbon nanotubes to expose carboxylate groups, and that causes these carbon nanotubes to become charged. And because of that, these neutral as well as charged characteristics of carbon nanotubes and their ability to then be sheared into very small sizes, these could be highly deleterious to the human health and of other organisms. Of course, there's much more that needs to be done, but for all of the positive aspects of carbon nanotubes, one needs to be careful about and be aware of what we don't know in science.